we reach the climax. Good. So let us begin. Welcome back with our quantum field theory discussion of free particles and free field quantization. Today we reach the climax of our build-up. Namely, we will finally discuss spin 1 and the massless case, the case of the photon and similar particles with spin 1. We have worked to this point for many weeks, and we had already many remarks concerning gauge invariance and concerning the special problems which are connected to this case, and so now we are able to discuss it. With our experience, we will actually be able to change the order of the subsections of this overall section a little bit, because we will not completely follow our standard blueprint, because instead we will directly jump to the critical points, because I think we will immediately be able to understand what are the important changes compared to the previous cases, and so in this way we will understand better this particular case. So today we will mainly be concerned with those critical extra discussions which are specific to the spin 1 massless case, and tomorrow we will collect everything and discuss it from the usual blueprint point of view. So today I want to begin in the following way, from 4 to 2 degrees of freedom.
طبعا في الفيديو السابق شرحنا هذا الانتقال من الفور to 2 degrees of freedom وعلى حساب البولاريزيشن، وذكرنا أنه البولاريزيشن يتعلق بالزاوية التي تتعلق بجيب التمام الزائدي والجيب الزائدي للزاوية. هذه الكميات تتعلق مباشرة بنظريتي، تتعلق بالدالة الأسية الموجودة في نظريتي، وهذه هي يقبع أهمية الأمر. طيب تعالوا نشوف المعادلة التي تخبرنا بهذا. هذه هي المعادلة، هي طبعا مختلفة عن المعادلة السابقة التي ذكرناها في الفيديو السابق. انظر MC سكوير هي الكتلة أو ما ضروب سرعة الضوء يساوي سرعة الضوء C4 على 4 R. R هو المساحة بتاعت التفاعل أو نسبة لقطر التفاعل أو المسافة التي يقع فيها التفاعل، مضروبة في الدالة اللوغاريتمية مضروبة في E أس ناقص 2 اللوغاريتم الطبيعي اللي سرعة الضوء 6 على 16 G ثابت نيوتن للجذب العام، وM الكتلة ممكن نعتبرها هنا طاقة التفاعل ناقص 10 GM على C تربيع R. يعني انظر إلى هناك كتلتين طبعا، الكتلة الصغيرة والكتلة الكبيرة. الكتلة الصغيرة هي الكتلة المطرودة من التفاعل، والكتلة الكبيرة هي الكتلة التي سببت هذا التفاعل أو ممكن نعتبرها طاقة التفاعل. انظر إلى ماذا؟ انظر إلى الدالة الأسية. الدالة الأسية هي عبارة عن السنش والكوش، لهذا أنا مهتم جدا بالبولاريزيشن والزاوية بين البولاريزيشن وعلاقتها بالنظرية أو تكون الكتلة وتطور الكتلة. في الفيديوهات السابقة، واحد الفيديوهات السابقة أنا حاولت أن أذهب إلى الإنترنت وأبحث عن ما يقوله العلماء عن الاستقطاب وما يقوله عن علاقته الاستقطاب علاقته بالكتل وتوزيع الكتل في الكون. كان رفقت فيديو يقولون أنه المادة المظلمة هي متوفرة كثيرا في الكون عن طريق دراسة الاستقطاب للأشعة الكونية الميكروية أو الخلفية الكونية الميكروية، وهذا يدل على كلامي. الآن سنهتم بالسبين زيرو التي هو عبارة عن الفوتون، وسنحاول أن نكتشف أيضا العلاقات بين زاوية الاستقطاب والمحور الاستقطاب، وذلك من أجل دراسة بعمق تكون الكتلة وتطور الكتلة الربط عن طريق هذه المعادلة. طيب تعالوا نواصل.
This is the first obvious discussion that we have already mentioned many times, because we know that our spin 1 vector field A mu has 4 components. However, we also know that a massless photon with spin 1 has 2 degrees of freedom, namely it has helicity plus or minus 1, and therefore we need to reduce the number of degrees of freedom somehow by 2. In the case of the massive spin 1 particle, we had to go from 4 to 3 degrees of freedom, and we did that by having a field A mu which was divergence free, d mu A mu equals 0. That equation reduced the number of degrees of freedom by 1 unit, but here we need to reduce the number by 2, and the question is, how can we do that? And let me just give you some very simple indication how you can go from 4 to 2 degrees of freedom in a 4-dimensional vector space sense. Namely, think of the Minkowski space, which has 4 dimensions. Minkowski space is the space where all the momenta in particular and all the polarization vectors epsilon mu, where they live. And how can you define in a physically sensible way a 2-dimensional subspace of the 4-dimensional Minkowski space? How can you do that? You can do it, of course, in many trivial ways, like you can consider the xy plane. That is for sure a 2-dimensional subspace, but that is not a covariant definition of a 2-dimensional subspace which is adapted to a particle which can have some non-vanishing momentum and which you want to rotate and which you want to Lorentz transform. So how can you define a 2-dimensional vector space which is connected to a particle motion and which is defined in a covariant way? So let us begin by first discussing a 3-dimensional and a 1-dimensional subspace. So if you have a momentum which is not entirely 0, so some momentum which has at least some non-vanishing components, then you can immediately define 2 very nice subspaces of Minkowski space that we already had. Namely, you can for sure define a space which I call a transverse space, which is the space of all the vectors which are orthogonal to p mu. So let's say all vectors v mu which are orthogonal to p mu. And if that p is not entirely 0, this defines a 3-dimensional subspace of Minkowski space, and the definition is covariant. So if you Lorentz transform the p mu, then all the v's get also Lorentz transformed, and you get a nice covariant transformation of this transverse space. So this would be the 3-dimensional transverse space. Similarly, you can also nicely define a 1-dimensional subspace, which I call VL, which is longitudinal, which is the space simply spanned by our p mu. So you can define the space of all the vectors which are proportional to p mu. This, of course, defines a 1-dimensional space of all the vectors proportional to p, and so we call that longitudinal. So that would be 1-dimensional longitudinal. All right. But how can you define a 2-dimensional space which is somehow covariantly connected to the vector p? Okay. So in order to understand that point, let us first consider the case that we already know, p square equal m square, which is non-zero. So now we go to specific cases of 4 vectors which are corresponding to a massive particle. That was the case that we already know. Then this VT is actually the space which is spanned by our epsilons for lambda equal 1, 2, 3, right? The epsilons were exactly a basis of all the vectors which are orthogonal to p mu. That was their definition. There are 3 linearly independent ones, and we made a specific choice, but that is now not important. Anyway, the 3 different epsilons for the massive vector field, they span exactly that transverse space. And we also know that the longitudinal space is independent of the transverse space, and so the p, the momentum, together with the 3 epsilons, they span the full 4-dimensional Minkowski space. So p is linearly independent of all the epsilons, and therefore the 4 epsilons plus p together give a basis of the full 4-dimensional space. So that was the massive case. What, however, happens if we now take the massless limit? Now p square equal 0. What happens in the p square equal 0 case? Something very special happens, namely what happens in this connection. Now p square is 0. That means p is orthogonal to itself, even though the 4-vector p is not 0, but p is orthogonal to itself. P square vanishes. What does that mean in this context? It means that the VL space is actually not linearly independent of the transverse space, but instead it's part of the transverse space. So in the massless case, this longitudinal space is a subspace of the transverse space, instead of being linearly independent. So and that of course also means that the 2 together, they do not span the full 4-dimensional space. They don't. They together just span the remaining transverse space. They only span a 3-dimensional subspace of Minkowski space. And if you would like to span the full Minkowski space, then it's not sufficient to take the basis of the transverse space plus p, but you need some 4th additional vector which is neither longitudinal nor transverse but something else. Don't. They together just span the remaining transverse space. They only span a 3-dimensional subspace of Minkowski space. And if you would like to span the full Minkowski space, then it's not sufficient to take the basis of the transverse space plus p, but you need some 4th additional vector which is neither longitudinal nor transverse but something else.
طبعا هذه المعلومة بغاية الأهمية، لأنه ممكن عن طريقها نحسب كتلة الفوتون، بحيث أنه نحسب كيف لأن أو مدى اعتماد اللونجيتيودينال أو الاستقطاب الموازي لكمية التحرك، مدى اعتماده على الاستقطاب العمودي. إذا وجدنا معادلة بهذه الآلية بحيث أنه تخبرنا هل هو فعلا اندبندنت ولا مستقطع ولا معتمد. إذا كان معتمد كليا فإن كتلة الضوء يساوي 0 فعلا، وإذا كان معتمدا جزئية فإن الضوء لديه كتلة. هذه طبعا يعني أداة جميلة جدا لحساب كتلة الضوء، أو أيضا ممكن حسابها عن طريق نظريتي، يمكن حسابها عن طريق نظريتي أيضا.
So later when we want a full basis, we need a basis vector which is neither this nor that. But at the moment we want to go from 4 to 2 degrees of freedom, and so how can we define a 2-dimensional space? And now we have a possibility. Now we have a possibility because here we have a three-dimensional space and here we have a one-dimensional subspace. And what can you do in linear algebra if you have a three-dimensional space and a one-dimensional subspace? You can define a quotient space. And that will be two-dimensional. So let me do it in the right words. So if we have now for all p mu which are not entirely zero and p square equals 0, we define now the following. So we can define a two-dimensional space which is a quotient space transverse divided by longitudinal. This is a quotient space of equivalence classes. Let me use this symbol here. Is this a familiar symbol for you for equivalence classes? Okay. So how are they defined? To just repeat everything, this definition in case you have forgotten what a quotient space is. It's a space of equivalence classes, and first of all, each representative that is allowed in this space needs to be orthogonal to p mu, and on the other hand, two vectors v mu and v prime mu are equivalent by definition if and only if the difference is an element of Vt, in other words, has the form A times P mu. So if two vectors differ by a multiple of the momentum, then they are called equivalent, and then all vectors which differ by such a multiple of the momentum form one equivalence class, and then this space here is two-dimensional and it is spanned by two equivalence classes. What would be a basis of that space? A basis would, for example, be the basis of the two transverse polarization vectors. So one would be this epsilon mu with lambda equal 1 from the massive case, and the other one epsilon with lambda equal 2. We can take over the definitions from the massive case without problems here, because these epsilons for lambda equal 1 and lambda equal 2, they are orthogonal to the four-dimensional p mu, and in the spatial part they are even also orthogonal to the spatial p mu, and so they are not multiples of the momentum p mu in 4 dimensions, and therefore they are non-vanishing basis elements of this space, and they are of course linearly independent. So this space here contains these two equivalence classes and all linear combinations of precisely these two equivalence classes, and so we have now defined a two-dimensional space. And the definition is clearly covariant because we have only used covariant objects to define our space. So the transverse space would undergo a covariant Lorentz transformation if you transform P, the longitudinal space of course also, and as a result this space of equivalence classes is also defined in a covariant way. So this is the first insight of today, namely you see now that it is actually possible to define such a covariant two-dimensional vector space, a subspace of Minkowski space. We, however, must be in the massless case. Only in the massless case this is possible, because only then the longitudinal is a subspace of the transverse space. So we need to be in the massless case. And in order to define our two-dimensional space, we need to have equivalence classes. So the key new idea that allows this construction is to introduce equivalence classes. So that is the first insight. Let us go to our second insight. we have already alluded to it. The last time we discussed a lot these polarization vectors epsilon mu, and they were quite important to define our vector field A mu, because they span a basis connected to the creation and annihilation operators. And so we can expect that in the massless case it is also useful to define such a basis of polarization vectors which are connected to a massless momentum. So let us think simply ahead of time already of such basis choices of polarization vectors. And let us immediately study their properties, because it's obvious that that will be useful. Massless polarization vectors. So the key problem that we already saw is in the massive case. We had a basis which spans the Minkowski space, which consisted of 3 different epsilons and the momentum. And so in particular there was the lambda equal 3 polarization vector and the momentum, and we already saw that if we take the massless limit or go to infinitely high energies, then those two become linearly dependent. The difference goes to 0. So they become linearly dependent, and therefore the basis, which consists of the 3 epsilons and the momentum, cannot be used in the massless case. We need to really do a discretely different choice if we want to have a basis of vectors spanning our Minkowski space. And so let us invent such a new basis. So it cannot be continuously different from that. It must be different in a discrete way. And so we just need to make now a different choice. And so actually I want to show you 2 choices. Let us begin with one of them. So this choice will have lambda equal 1, 2, 3, and 0 for epsilons for these 3 lambdas. And let me immediately write down what is this choice, because it's not difficult to grasp why it works. So for lambda equal 1, we simply choose the same as before. So we have here a spatial vector epsilon 1, which is orthogonal to the spatial momentum. And for lambda equal 2, exactly the same. And of course there is a basis of 2 linearly, or in fact 2 orthogonal vector epsilons, which are also orthogonal to P. And we don't need to specify them explicitly, but it's clear that they exist and they are normalized and orthogonal to P. Okay, but so that is the same as before. But now let's think about the other 2 for lambda equal 3 and for lambda equal 0. What could be a third polarization vector, which is first of all linearly independent of these 2, but also which spans then the full space together with the 4th one. And so one possibility is simply this. In the third case, we still have here a 0 in the first component, and then we have here, instead of those 2, we have the unit vector in momentum direction EP. Then it's clear that those 3 are already orthogonal to each other. They are all normalized in exactly the same way. So that is certainly a good choice, and also a viable one. And then the question remains, what is the 4th basis vector? And now you probably see what is necessary. We need something that has a non-zero entry there. And so one simple choice, our choice, is simply that one, 1, 0. And then this last one is defined in a way which is not covariant. It's whatever we choose for P, the fourth epsilon is always this. So it is not Lorentz covariantly defined. It is defined explicitly always in this way with 1, 0, no matter what momentum we have. But anyway, this is a good basis choice. It's clear that it's a basis, and not only is it a basis, but it also satisfies some obvious completeness and orthogonality relations, namely the same as for the massive case. So we have here this epsilon mu of P and lambda contracted with epsilon mu for the same P but lambda prime. Then you see that they are all mutually orthogonal. So we always get 0 if we multiply two different ones. And if we multiply the same, then in these three cases, the product of itself gives -1, because here in the spatial part we have a unit vector. And in that case, we get +1. So that can be again written as this G lambda lambda prime. So we get +1 for this case and -1 for all the other cases in the normalization. And then we also have a completeness relation, sum over lambda from 0 to 3 of epsilon mu with the same lambda and the same P and open Lorentz indices mu. And what is the result of this? It is -G mu, actually plus. And how can we prove it? We prove it again by trying whether the left-hand side and the right-hand side gives the same when we apply it to all basis vectors. And that is now extremely simple and obvious because all the basis vectors have this simple normalization. And so if you multiply that and this with the epsilons, it was. And here you need to put in this G lambda lambda prime. That means that the epsilons, they enter either with plus or with minus, depending on the lambda. And then indeed you see that this works, because then if you apply it to any one of the basis vectors, you get from the product here G lambda lambda prime times the other G lambda lambda prime gives exactly 1, and then the other epsilon remains. So this basis satisfies these simple orthogonality and completeness relations. And therefore, it is a very useful basis, in particular if we later connect it to creation and annihilation operators, which then also will have simple orthogonality on properties, which means commutation relations. Yes? Okay, yes. G lambda lambda. And of course, yes. Here no lambda is not summed over in this alone, but it's an explicit number. Other questions? So this is one basis, and however, it's not the only useful basis because it has a nice advantage. However, it also has a very, very obvious disadvantage. What is the obvious disadvantage of that basis? Right, that is a very obvious disadvantage, and it is connected to something else. It is really not connected at all to the massive case, and in particular the basis does not contain the momentum 4 vector. And it is nice for various reasons if the momentum 4 vector is somehow contained in our choice of the basis vectors. And so that would then also covariantly Lorentz transform. So let us choose an alternative basis which takes this into account. an alternative basis for p mu, and I will call it the 1, 2, ls basis. So instead of the 3 and 0 vectors, we will define two new basis vectors, which I call ls, and the 1 and 2, they remain. So the new one, epsilon mu for p and lambda equal L. L stands for longitudinal, and that is proportional to the momentum p mu, and I write it as 1, EP. Okay? So it's not exactly the momentum, but it's kind of normalized. And so you can also write it as the momentum for vector p mu divided by the p0 component. So it's also not completely Lorentz covariantly defined, but at least it's proportional to the covariant p mu. But it has this normalization. And then we define epsilon p with lambda equal to s. And that is now the fourth basis vector, which must be linearly independent of all the other three. And so there is no way, at least I do not know of any way, to define it in a covariant way, and therefore we just do something which is linearly independent of the rest, and we do 1 and minus EP. And then this basis is useful because it contains this vector which is proportional to the momentum, but it has some disadvantages, in particular the orthogonality and completeness. They are much more complicated. And let me just write down an example. So for example, epsilon mu with S, epsilon mu with L. What is this product of those two different polarization vectors? This is now not 0, but what is it? Yep, it's 2, exactly. So they are not orthogonal, but they are linearly independent, but not orthogonal to each other. And the other thing, which is also noteworthy, if you do p mu times epsilon mu for any of the lambdas, then what do you get? So p mu times epsilon mu for lambda equal 1 and 2. What do you get? P mu times epsilon for lambda equal 1 or 2? Those ones. That is of course 0. Right? So that is 0. What happens if you do p mu times the longitudinal epsilon? P mu times the longitudinal epsilon. What is that? It is of course also 0. It's also 0. Okay. What happens if you do p mu times the S? S stands for scalar. For the scalar epsilon, what is then the result? Then you do not get 0, but instead you get p mu p0 plus p0 then gives 2 times p0. That is compatible with this result here, because it's the same up to the factor p0. So you see, the epsilons are not mutually orthogonal, and also not all of them are orthogonal to p mu. They can't be all orthogonal to p mu, of course. But the scalar one here is not. So this is our two alternative basis choices, and each of those two basis choices will be useful and important for some purposes, and that is why we want to have both in mind. And I mean, you know, it's a basis, and therefore if you have a basis expansion of some object in this basis vectors, then of course you can equivalently rewrite the coefficients by going from one basis to the other. So, but now we need to do a last point on the polarization vectors, namely we want to look at the Lorentz transformations. That is very important because we want to study afterwards the Lorentz transformation properties of our vector field, let's say an A mu field operator. How would that Lorentz transform? And clearly it must be useful to first know how the epsilons transform. And we have tried to make them as covariant as possible, but they are clearly, as we discussed, not all completely covariant. So that is not covariant for sure, and also the epsilon s is not completely covariant. So how do the epsilons behave under Lorentz? Let us do it in this alternative basis only. And since they are equivalent, you could from that derive how the other epsilons Lorentz transform. And so we look at epsilon prime mu is defined as lambda mu nu times epsilon nu for any polarization vector. And we also have p prime nu is equal to lambda mu nu times p nu. And then the question is, how are the Lorentz transformed epsilons related to the polarization vectors of the transformed momentum? That is really our question. So we have on the one side epsilon prime mu of p comma lambda. Okay? So you take an epsilon, do a Lorentz transformation, and on the other side you can ask how does it relate to the epsilon of p prime for some lambda prime. If the epsilons were defined in a fully covariant way, then we would simply say epsilon prime is equal to lambda mu nu times epsilon. Maybe this. So the simplest case would be this. All the epsilons are defined in a covariant way. So epsilon prime for one lambda is equal to lambda times epsilon of p prime for the same lambda. That would be a covariant behavior. And of course that is not the case. It is not the case. It was not even the case for the massive case, but here it's even more complicated. But we have 4 linearly independent epsilons. So they span the full 4-dimensional space, and therefore what we definitely know is that there must be some linear combination C lambda lambda prime such that the Lorentz transform epsilon for one lambda is a linear combination. That here is unnecessary. That here is unnecessary. It's just a linear combination of the polarization vectors for our transformed momentum. Such an expansion must exist because these 4, they span a basis of the 4-dimensional space, and therefore the epsilon prime must have some expansion in those 4 epsilons. So there must be such a sum lambda equal 1 to Ls of a matrix C lambda lambda prime. And this matrix C lambda lambda prime is of course a matrix which depends on the momentum P that we start from, and it also depends on the Lorentz transformation lambda that we do. But anyway, the matrix must exist. It has 2 indices, lambda lambda prime, which run over the 4 basis vectors, and then we can re-expand our Lorentz transform polarization vector. And now what we want to discuss is what are the properties of that matrix. In other words, which epsilon transforms into which. And that we can sketch. Let us just sketch the non-vanishing matrix elements. So hopefully a kind of self-explanatory schematic notation. So if we take, for example, on the left lambda equal L, okay? So let's just write it in this schematic way. On the left you have lambda equal L, and then you do a Lorentz transformation. In other words, I ask myself in this equation here, which of the coefficients are non-zero if I take lambda equal to L? lambda equal to L means that our epsilon is actually p mu itself divided by some normalization factor. But if you do a Lorentz transformation, then here on the left you would get lambda mu nu times p nu, that is p prime mu, the Lorentz transformed 4 vector p prime. That is what you get on the left. And so what is then the expansion of that p prime mu in terms of the polarization vectors specific for the momentum p prime? Which of the 4 appears? Are you still with me? Oh, yes.
Lambda equals L1.
Right. Only the lambda equal L1 appears. So what I mean by this, let me write it just once. So epsilon prime mu of p comma lambda is equal to p prime mu divided by p without prime 0, and that is equal to epsilon mu of p prime comma L times p0 prime over p0. So that is what I really mean. Okay. That is what I mean. So if we have lambda L and Lorentz transform it, you get only epsilon with lambda equal L on the right. Now let's do it for all the other cases in a similar way. What happens if you start out with lambda equal 1 or 2? What happens if you start out with lambda equal 1 or 2? If you start with lambda equal 1 or 2, you have a polarization vector which is orthogonal to p mu. So epsilon dot p equals 0. That is what you start out with. So then you do a Lorentz transformation, then you know that the Lorentz transformed epsilon prime times p prime is still 0. What does that mean for our basis expansion? If you want to expand this epsilon prime in terms of our new basis, then only basis vectors may appear which are themselves orthogonal to p prime. So which basis vectors are orthogonal to p prime? Only 1, 2, and L, but not S. So it's clear that the scalar epsilon, which is the only one which is not orthogonal to p, that cannot appear in the expansion. So S is missing here. That is the information. So L goes to L, 1, 2 goes to 1, 2, and L. So is the L here necessary? Or could it be that maybe the 1, 2 only transform into 1, 2 themselves, but the L is unnecessary here? It's in general necessary. We cannot do anything about it. We see it, for example, by doing a Lorentz transformation of the epsilons with lambda equal 1. We have a 0 in the 0 component, and in a general Lorentz transformation we will always produce a non-zero entry in the 0 component. Therefore it's clear that we must in the basis expansion have at least one basis vector which has a non-zero entry in the 0 component. Therefore it's clear that that is in general necessary. So and what about S? About S we know nothing, and it can just go into anything. So there is no information that we can get from this. And so that is what we know. So this is how our basis vectors transform. And so in the case of Lorentz transformation, the alternative basis behaves in a simpler way, in particular because of L to L only, and so on. And so we have this kind of information. So now we have polarization vectors for massless momenta. And now we can go and discuss immediately the quantum theory of a field operator for a massless spin 1 particle. So that is our section 263, the expected Poincare properties. Okay, so bypassing all the blueprint typical derivations, it is clear that at the end we will have a field operator. So we expect that we will get some field operator A mu hat of x. And what do we expect this field operator to look like? We surely expect it to start with a dp tilde integration measure, which implements the equation that p square is equal to 0. Then we expect a sum over lambda for the different polarization vectors, and then we have here epsilon mu of p comma lambda times some operators a of p comma lambda times e to the minus ipx plus the Hermitian conjugate of the same thing. That is what we always had, and it is quite clear that we should get something similar now. And in the case of the massive field, the lambdas extended over 1, 2, 3, the three polarization vectors which are orthogonal to P in order to implement this Lorentz gauge condition, which was a consequence of the proper equation. But here we do not yet know, so let us simply write here first lambda equals 0 up to 3. And maybe, like in the massive case, not all the lambdas are important, then it would just mean that some of the operators here could be set to 0 without problem. So we remain completely general at this point, and we can set operators to 0 later. But we expect some operator like this to appear. And of course, as always, we also expect in our theory a unitary representation of the Poincaré group. So we also expect that we have operators U of lambda and A. And they should generate Lorentz transformations on our Hilbert space of states. And they should also generate Lorentz and Poincaré transformations of the field operator. It was always like that. So let us write down the expected relationship. The expected relationship is this one, U dagger of lambda A times A hat of lambda x plus A times U without dagger of lambda A. This essentially generates a Poincaré transformation of the field operator, and if that field operator has the property of being a real 4-vector field operator, then it has a certain Poincaré transformation, namely that must be lambda mu mu times A mu at x. So this is the direct generalization of what we always had in all the previous cases. And let us study this expectation. What can we learn if that is true? Then we get a lot of information, and let us evaluate that information with our previous knowledge of how the epsilons Lorentz transform and the physics of spin 1 particles. We can extract all of this information from that expectation here. Okay. So the first consequence that we can draw from that expected property of Lorentz transformations and the field operator is what we always did also in the scalar case and spin 1/2 case. What is the spin of the particles that are created by this field operator? So we have here A and A dagger. They, of course, will generate one particle states, multi-particle states in our Hilbert space. And we always asked, what is the spin of those states? And what did we do? We looked at a one particle state and acted on it with an angular momentum operator. And how did we know how the angular momentum operator acts? We know it from this equation. That equation exactly tells us the Lorentz transformation of those A daggers, and therefore it also tells us the Lorentz transformation of the states created by the A daggers. And so from this we always could conclude how the actual A daggers Lorentz transform, and we got it by looking at the Fourier coefficients in front of, for example, e to the ipx. If you look at this equation and extract the Fourier coefficient in front of e to the ipx, then you get the Lorentz transformation of the A daggers. So if we do that here, what actually happens. So on the left hand side of the equation, in front of the e to the ipx, we have a sum over lambda from 0 to 3. Then we have an epsilon mu of p comma lambda. And then we have u dagger and u, and in between we have our creation operator. Let me just drop the arguments. U dagger of a dagger of p prime and lambda and u. Okay. Why p prime? And here also p prime. Why p prime? Because our field a hat is evaluated at the primed argument, and so we can also do a variable substitution in the exponential function. So we have here p prime. And on the right hand side of the equation, what do we have here? Sum over lambda from 0 to 3, and here we simply have lambda mu nu times epsilon mu of p comma lambda times a dagger also of p comma lambda. I need to drop the arguments. That is our equation, and so we can read off from here what is the Lorentz transformation property and Poincaré of the a dagger. Actually, let me drop the translations. Let me only do it for Lorentz transformations. So let us make the equation a little bit nicer by relabeling the dummy index lambda here. Let's call it lambda prime. Then we have here lambda prime everywhere, but on the right hand side let us leave the lambda. And then we have on the left hand side a sum over lambda prime, and we have Lorentz transformations in operator sense of a dagger of lambda prime. And on the right hand side we have a linear combination of a daggers of lambda. So we get that the Lorentz transformation of such a creation operator is a linear combination of other creation operators. That is what we get. And so let us now evaluate this. Maybe let's maybe squeeze here one more line, and then we have here a nicer conclusion on the new blackboard. So we have here a sum over lambda and lambda prime, because this here is now a sum over our epsilon primes, the Lorentz transform polarization vectors, right? That appears on the right hand side. For the Lorentz transform polarization vectors, they can be written as a linear combination of the original polarization vectors at the new momentum. And so we can now insert exactly that equation over there. And then instead of this, we get a sum over lambda prime with this matrix C lambda prime times epsilon mu of p prime comma lambda prime a dagger of p comma lambda. And there you have it. On the left hand side we have a sum and a linear combination of epsilons of p prime and lambda prime, and on the right hand side we also have a linear combination of epsilons of p prime and lambda prime, and therefore those are four linearly independent numerical four vectors, and therefore the coefficient of each epsilon polarization vector for each lambda prime must be the same on the left hand side and the right hand side of the equation. And then we can read off directly the Lorentz transformation of this, because that is one coefficient of one such epsilon. And if we look at the coefficient of the same epsilon on the right, then we get exactly the result of that operation. And that is what I want to write down now. So we need to look at the coefficient of the epsilons of p prime and lambda prime, and then on the left hand side we get u dagger of lambda times a dagger of, let's say, p comma lambda prime, p prime and lambda prime, and u of lambda. And on the right hand side we get only the sum over lambda without prime, matrix C lambda lambda prime, and a dagger of p and lambda. So here you see how our creation operators Lorentz transform, and they Lorentz transform into linear combinations of original creation operators multiplied with a matrix, and that matrix is the same matrix as the one that appears in the transformation of the epsilons. So if we work in the basis with L and S, then it's simpler, and then we have creation operators corresponding to this L and S polarization, and they will have this simple Lorentz transformation. And let us write down again what are the non-vanishing contributions in a similar schematic way as above. And so you see here that the transpose matrix actually is relevant. So here lambda prime goes to lambda, but with C lambda lambda prime. So it's the transpose matrix which is now relevant. So suppose we have here on the left hand side S. Here we have S. And then we do this U dagger and U transformation from the left and right of the corresponding creation operator. So it means lambda prime is now S. And what are the non-vanishing terms? The non-vanishing terms are the ones where here on the right where S appears. S appears only here. Here lambda prime is S. And that appears only in one place, namely it appears only in the place where lambda is S as well. So that tells us here, if lambda prime is S in the sum over lambda, we only get one contribution from the S itself. So a dagger of S transforms only into a dagger of S. So it's kind of Lorentz invariant in a certain sense. How about the others? So for example, how about L? L, lambda prime is now L. Lambda prime is L. So we need to look where is here L appearing in the lambda prime column. L appears everywhere. That means C can be non-zero if lambda prime is L for any lambda. That means L could go into 1 to SL into anything. And in particular, I asked this before, is it really true that on the right hand side this 1 and 2 appears with a non-zero coefficient? Yes, because we already said at the same place here, here, 1, 2 will definitely go into L with a non-vanishing coefficient. That is necessary, and for the same reason we have here 1, 2 appearing with non-zero coefficients. They are the same non-zero coefficients here. So L will mix into 1 and 2. And what about 1 and 2? 1 and 2 appear here. They can go into 1 and 2, but they also appear there. So they can go into S. 1 and 2 can go into S, but not into L. So these are the non-vanishing Lorentz transformations of our creation or annihilation operators. So that is interesting to know. And the next physical question that we want to tackle is really what is the physical nature of the particles that are described by this quantum field and by the creation operators. And maybe or maybe not, you can already guess that the 1, 2 entries correspond to the physical states, to the transverse states of the photon, whereas this S and L, they are kind of unphysical. So therefore, let us first focus on the behavior of 1 and 2, and the outcome will indeed be that these have the properties of a massless spin 1 particle or like the photon. But let's prove it. And we prove it exactly in the same way as we always did it, by going not into the rest frame but into a simple frame. And then we act with angular momentum operators onto particles in that frame, and we see what happens. And the outcome will be spin 1. So that is the question, the physical meaning of the polarizations lambda equals 1 and 2. And so what do? We go to a special frame where the momentum of our massless particles is this p0, 0, p. That means we move in the z direction with the speed of light. Then we use, in this case, we go back to our other basis, to the first basis, then the sum over lambda from 0 to 3 of this epsilon and a dagger. How does this sum actually look like? You know, the polarization vectors for that particular momentum, they are very, very simple in this first basis, because the epsilon 1 is simply, so they are just unit vectors, all of them. All the polarization vectors are simply 0, 0, 0, 1 and 1, 1, 1, 0, 0 and so on. So for lambda equals 0, the epsilon had this 1, 0, 0, 0. So if you multiply them in the upper component, we get a dagger of 0. Then our epsilon with lambda equal 1 is the vector 0, 1, 0, 0. So we get here in the second component a dagger of 1. Then the polarization vector for lambda equal 2 is 0, 0, 1, 0. So we get here a dagger of 2. And for lambda equal 3, we get 0, 0, 0, 1. And so that is very simply how this sum looks, explicitly written down. So therefore we have at our disposal immediately all the 4 different a dagger operators. And that, of course, would go into our field operator at the top of the other blackboard. So you can imagine that sum here looks now like this. Then we consider rotation around the z-axis, jz, which is of course an abbreviation for j12, and a Lorentz transformation, lambda, which is actually a rotation around the z-axis. How does the 4x4 Lorentz transformation look like, which corresponds to that rotation? It's the following. So in the 0, 0 component we have 1, and then we have here cosine theta minus sine theta plus sine theta cosine theta, and then here again a 1. That generates a rotation around the z-axis with the angle theta, and so that corresponds in our infinitesimal form omega 1, 2. Omega 1, 2 is the infinitesimal element here in this 1, 2 element. The infinitesimal term here, omega 1, 2, is now minus theta, and so that means omega 1, 2 with lower index is plus theta. And then it means our u of lambda, which is always unit operator minus I over 2 omega mu nu j mu nu. Now only this omega 1, 2 is non-zero, and it's actually plus theta. So we get here 1 minus I theta prime times jz. So the 1/2 drops out because omega 1, 2 is equal to minus omega 2, 1. Okay, so we have then everything very explicitly in front of us. All the matrices, all the operators are completely written down explicitly, and so we can now really the action of our U transformation onto the generators. So U dagger of lambda times the sum over epsilon and A dagger. So like here on the blackboard, A dagger of 0 up to A dagger of 3 times U of lambda. That should now be equal to the Lorentz transformation lambda mu times A dagger of 0 and so on up to A dagger of 3. Maybe it's too long-winded and too detailed what we are doing here, but you should really see now totally explicitly what happens. So here this U dagger of lambda is now 1 plus I theta JC. That is 1 minus I theta JC, and that is the unit matrix omega delta mu plus omega mu, and in omega mu we only have one non-vanishing entry, which is the omega 1, 2, which is theta. So therefore, in order theta, you can now read off what happens. So in order theta, we have on the left-hand side I times theta times the commutator of JC with all those operators, A dagger of 0 up to A dagger of 3. That is what happens on the left-hand side. And what happens on the right-hand side in order theta? In order theta on the right-hand side, so we get here nothing in order theta in that component. We get nothing in the lowest component, but we only get something non-zero in the middle two components, and in the upper component we get minus theta times A dagger of 2, so it's reversed, and in this component we get plus theta times A dagger of 1. Now, super explicit calculation, but it allows you to read off explicitly all the commutators. Commutator of JC with A dagger of 0 vanishes. Commutator of JC with A dagger of 3 vanishes. Commutator of JC with A dagger of 1 gives minus A dagger of 2. So we have to multiply with I minus I. Then did I make a mistake? No. Okay, so therefore, maybe let's just squeeze here into that box the final result, namely a commutator of JC with A dagger of 1. So let's leave here some space. Commutator of JC with A dagger of 1 multiplied with minus I gives plus I times A dagger of 2. Plus I times A dagger of 2. Let's leave here some space. And the commutator of JC with A dagger of 2 gives minus I times A dagger of 1. And so we can combine them by saying commutator of this with A dagger of 1 plus minus I times A dagger of 2. Then we can write down both immediately. So this here gives that, and then we have here plus or minus A dagger of 1 plus or minus I times A dagger of 2. So we can check it. So A dagger of 1 gives always I times A dagger of 2, and plus minus I A dagger of 2 gives plus minus A dagger of 1. How does that look like? It looks like this linear combination of operators generates an eigenstate of the operator JC with eigenvalue plus 1, and the linear combination with minus generates an eigenstate of JC with eigenvalue minus 1. So these operators generate JC eigenstates, and the eigenvalues are plus minus 1. So let us write that down on a nice blackboard. That shows you that those operators here create photon states or spin 1 massless particle states, which have the correct property. Namely, we already know from Poincaré discussions that only helicity counts for massless particles, and we have a particle which moves with the speed of light in z direction, and we look at the angular momentum in z direction. That is the helicity. So we see that those operators composed out of lambda equal 1 and 2, they generate eigenstates of helicity with eigenvalues plus minus 1. That are exactly the states which are physical and which are physically necessary. So let us write the conclusion as a kind of nice text. So we get two linearly independent creation operators, A dagger 1 plus minus I times A dagger of 2 for states with eigenvalues of helicity, which is the spin in p direction, with helicity equal to plus or minus 1. And it is quite clear from the construction that this would hold not only for this particular momentum in z direction, but it would hold completely analogously for any momentum in any direction. Because in our basis, the lambda equal 1 and 2, they are orthogonal to the p momentum in the spatial part of the forward vector, and that is what guarantees this property here. And so the two physical degrees of freedom of a massless particle with helicity or spin plus minus 1 they are described by the lambda equal 1 and 2 part of our formalism. So actually, the creation and annihilation operators for lambda equal 1 and 2, they are completely sufficient. They are sufficient and necessary to describe correctly a massless spin 1 particle, like a photon. And that is nice. We have understood the meaning of this lambda equal 1 and 2. We have explicitly looked at the rotational properties of those states. They are exactly the correct ones. But now, of course, this raises the question, what about the other operators that we have in our formalism for lambda equals 0 and 3? They are apparently not necessary to describe the spin 1 particle, so they are kind of unphysical. We have no interpretation for them yet. And in fact, they will remain unphysical. They are unphysical, they are not necessary to describe physical states, but they are necessary in our formalism for various reasons and to fulfill various properties. Let us spend another few minutes on discussing, instead of lambda equal 1 and 2, let us discuss also lambda equal s, this scalar degree of freedom. That is also easy to interpret. You can understand where it comes from and what it means and what is its role quite easily. And a key property you see above at the upper blackboard still, namely S goes only into S. What does that mean? if you start out with a S particle or with a state of S height, you do a Poincare transformation, it remains S. I already told you S stands for scalar. So that is like the property of a spin zero state. A spin zero state, if you transform it, it has only one single degree of freedom, it remains this degree of freedom. So this behaves like a scalar field, and it somehow would correspond to spin zero. So let us make that a little bit more explicit. So that way delta S goes under U of lambda just to something proportional to A dagger of S. And you can understand why this is the case in a very simple and useful way. Namely, please look at the following combination. D mu A mu, which was zero in the massive case, right? That was zero in the massive case, but now in the massless case, we don't know what that is. But it looks for sure Lorentz invariant. That looks like a Lorentz invariant or covariant object. It looks like a scalar field. This looks like a scalar field. And behaves as a scalar field. And but what is it actually? If we plug in the expansion that was on some of the blackboards, the expansion, dp tilde integral, and then the sum over lambda, can you do it on your own? What happens if you contract with d mu? What happens in our sum over lambda? So the d mu in the integral, it hits the exponential function e to the minus ipx. So therefore the d mu effectively becomes minus ip mu. So then inside of the integral you have a contraction of p mu with the epsilons, p mu times epsilon mu. So p mu times epsilon mu is often zero. Then those terms where it's zero do not contribute. Which of the terms are non-zero? In the alternative basis, it's only the lambda equal S term. So only the lambda equal S term in the alternative basis remains. And so then we get the contraction of that lambda equals, so maybe let's write it down. So the sum doesn't exist anymore. There is only lambda equal S, we have minus I. And then P mu times epsilon mu of P and lambda equal S only. Then times A of P comma S, e to the minus IPX, plus the same emission conjugate term. And so that contraction is whatever it is. What is it? It depends on our normalization of this epsilon mu, and the result was 2 times the energy, 2 times P0. So we have minus 2I P0 times A of P comma S e to the minus IPX. That's the Hermitian conjugate of this. And so now d mu A mu, the operator, really looks like a scalar field operator expansion, but the creation operators for that scalar field, they have now an unusual normalization, basically minus IP0 times A. That takes the role of our creation annihilation operator of our scalar field. And so, but up to that normalization, which is not important, you see that this A of S just behaves like the creation operator for a scalar field, a Klein-Gordon field, which describes a spin zero particle. Let's write the name Klein-Gordon field operator. This is a creation operator proportional to A dagger of P comma S. And so that shows you that the A dagger of P comma S with the S labeled the scalar would describe something like a spin zero state. And it might also depend on what we want, but if we want to describe a massless spin 1 particle, then we do not want to describe those spin 0 particles which are created by this A dagger of S, so we would call them unphysical. And we have to remove them from our theory. For example, we have to remove them somehow from our Hilbert space of states.
طبعا هنا ذكر المحاضر انه هذا السكيلر يعتبر انفيزيكال لانه نحن ندرس سبين 1. في الواقع في الطبيعة يعني احنا لا ندرس سبين 1. يعني عندما ننظر الى الكون وننظر البولاريزيشنز في الكون نحن لا ندرس سبين 1، نحن ندرس الجسيمات كلها بما فيها سبين 0. فلهذا يعتبر هذا النوع من البولاريزيشن بالنسبة لنا ذو أهمية قصوى. يعني عندما ندرس توفير المادة المنظمة، الطاقة المنظمة، الجزيئات، الذرات في الكون ككل، يجب أن نأخذ هذه السكيلر بعين الاعتبار. لكن السبين 0 معروف أنه لا يظهر العيان، لا يظهر إلى يعني كفيري بارتيكل، إنما يظهر في التفاعلات الداخلية فقط، اللي هو مثل هيجز، مثل زي وهكذا. إذن نحن ما نرى منه غير الانحلالات التي تحصل له في ذلك الفضاء. لكن هناك أمر مهم أريد أن أقوله: ماذا يحدث إذا كان هذا الجسيم موجود؟ وطبعا انحلال هذا الجسيم حسب فرضيتي أنه كتلته تتضخم أو طاقته تتضخم أثناء بعد التفاعل وخارج من التفاعل، من وسط التفاعل لأطراف التفاعل، فإنه يعتبر تهديد للفضاء ثنائي الأبعاد، وبالتالي الفضاء ثنائي الأبعاد يحلله مرة أخرى. طيب ماذا يحدث إذا كان هذا الجسيم لا يمثل تهديد الفضاء ثنائي الأبعاد؟ إذن سنرى شيئا غاية الأهمية، وهو ربما نجده في ذلك الفضاء كهيئة من هيئات المادة. يعني في الفضاء الخارجي ربما نجد سبين 0 والهيجز كهيئة من هيئات المادة. والمادة لدينا نوعين من المادة، فيرميون وبوزون. والبوزون حامل للقوة التي تظهر للعيان، والبوزون والفيرميون يظهر للعيان. في البوزونات لدينا بوزون واحد يظهر للعيان هو الفوتون. فما الذي يجعل يمنع انه الجسيم هيجز يكون واحد من تلك الفوتونات لكن بسبين 0؟ ما الذي يجعل ذلك؟ طبعا السبين يمنع ذلك. إذا كانت طاقتك عالية فإن السبين لا يمكن أن تكون 0. إذن يمكن أن نرى جسيم هيجز كسبين ليس سبين 0، أو أنه يتحلل إلى مواد أخرى في الكون كما ذكرت، لأن السبين يعتمد على ثقل الجسيم وعلى الفضاء ثنائي الأبعاد الدفاع النفسي. فسبين 0 ربما يكون لديه هذه الخاصية. لكن ما أريد أن أقول أنه سبين 0 هو مهم جدا، البولاريزيشن إكس هو مهم جدا في دراستنا لهذا الكون، وربما نبحث عنه في المستقبل.
I told you in the beginning, with our experience we could immediately jump to certain critical points in our derivation, and so that was of course the center of our today's discussion. We have now seen various critical points, namely how is a massless spin 1 particle contained in such an A mu field operator, and how is the role of the 4 different creation operators A dagger of lambda, how is it connected to the physical particles that we have. And let me now draw some conclusions from the discussion. in the sense that we write now down the problems that we see that we are faced with when we quantize spin 1 particles and fields. So let us start from this. If our field operator A mu really behaves in the way that we have just discussed, okay, that was an expectation, okay, it was an expectation, and if the expectation is true, then we have already derived the consequences, and now let us spell it out explicitly. So if that is true, what we have just described, then it means that this A dagger of S and A dagger of L, they are unphysical. They create unphysical states. So that is then the fact of life. The A dagger of S corresponds to spin 0, which we don't want, and the A dagger of L that has no interpretation at all. But anyway, both are unphysical. And that is not even our only problem, because we already saw some lectures ago that we also expect anyway something else, namely if we have a Lorentz covariant A mu field operator, which we now assume to have, then we expect negative norm in our Hilbert space, because the A mu, A nu, that would give rise to matrix elements that behave like G mu nu, the metric tensor, with positive and negative entries. Therefore, we expect negative norm, which is also a problem. So that was in section. And that is not even our only problem, because we already saw some lectures ago that we also expect anyway something else, namely if we have a Lorentz covariant A mu field operator, which we now assume to have, then we expect negative norm in our Hilbert space, because the A mu, A nu, that would give rise to matrix elements that behave like G mu nu, the metric tensor, with positive and negative entries. Therefore, we expect negative norm, which is also a problem. So that was in section 251. So, but the good thing about this expectation is that we assume the field to be Lorentz covariant, and so that is certainly nice. And the Lorentz transformation properties, we have discussed them, and so they told us that A dagger of 1 and 2, the physical polarization, they transform under U of lambda to A dagger of 1, 2, and S. So they transform from something physical into something non-physical, and if we start with L, then we go to 1 and 2 and L. So out of something unphysical via Lorentz, we create something physical. And therefore there is a mixing between physical and unphysical degrees of freedom under these Lorentz transformations. Unphysical and physical degrees of freedom mix under U of lambda. So that is one problem. Unphysical states, and they mix within Lorentz transformations. So, and basically the equivalent problem can be formulated in the opposite way. Namely, you could now say, okay, our discussion tells us that we have unphysical degrees of freedom which we don't want. So let's throw them away. Okay, let's throw them away. Let's say we don't have them. So let's try to remove them. Let's try to remove a dagger of L and S. And that would mean in our quantum field operator that we simply say, let's say we define a physical A mu operator, A mu physical, which is then the same expansion, but we sum only over lambda equal 1 and 2 times the rest. Okay. We simply drop the unphysical terms in our field operator A mu. Okay, what happens then? Then, nicely in our theory, we only have physical particle states for physical polarizations of a spin 1 massless particle. But we encounter some other problem, namely which problem do we encounter? Of course, this operator is now not Lorentz covariant anymore because we have dropped something which mixes under Lorentz transformations with the physical degrees of freedom. So this thing cannot have this typical Lorentz transformation that it goes under u of lambda into lambda mu nu times a nu. So let us make that explicit and let us make explicit what happens instead. So let's say so assume that the Lorentz transformations of a dagger of lambda equal 1 and 2 remain, because we have seen from our little discussion that the Lorentz transformation properties of those two, they are correct in the sense that they are really the ones for a massless spin 1 particle. So that is nice. So let us keep those Lorentz transformations, but simply set the others to 0, A, L, and S. Simply set them to 0 by hand. If we do that, then one thing is not so problematic, namely actually this A dagger of T, S equals 0, that is kind of okay, because you see that if you, we don't see it anymore, if you set it to 0 in the Lorentz transformations, it is consistent. Because you could set it to 0 on the right hand side of some Lorentz transformations, then you simply say the operator is 0. And if you have it on the left hand side, then it transforms into itself, so 0 goes into 0. That is also consistent. So that is actually consistent. However, if you set the L to 0, that is not consistent, because under Lorentz, L must go into 1 and 2. So if you set the L to 0, but it must transform into 1 and 2, then you have a contradiction. You cannot have that the Lorentz transformation of 0 is a certain well-defined linear combination of 1 and 2. And that is the inconsistency. And time is very short, so but maybe we just figure it out. What is the resulting problem? Difficult to figure out what is the problem, because we simply look at the Lorentz transformation behavior of this AL on its own. That is then missing, and whatever the L contributes will be the mistake. So the mismatch is now the following. Let us simply look at this Q dagger of lambda, and we take our field operator, only the term from the L generators of lambda x times u of lambda. And then we have here our integral dp tilde. And then the sum over lambda okay, or first let's say no sum over lambda, but we only consider the term epsilon mu p prime L, then mu dagger of lambda A of P prime L, Q of lambda plus the Hermitian conjugate times e to the minus IPX. Okay, and then we already know what is the Lorentz transformation of this A of L. So it is, of course, a sum over lambda of this C L lambda, this matrix times A of P prime of lambda. And the epsilon of L, we can actually plug it in. So that is a prefactor times P mu, or P prime mu. So that is lambda mu times P mu. Sorry to rush a little bit. Sum over lambda CL lambda A of P prime lambda e to the minus IPX. But the main point is now very simply the following. We can write the P, which appears here as a prefactor, and of course we need to divide by 1 over P prime 0. But the P can be written as a derivative, and that can be pulled out of the integral. So this is I times d by dx mu lambda mu times some object. And let me now abbreviate our lives by not writing down the rest. But this can be written as a derivative, and therefore the whole thing, the lambda mu is not important. So it can be written as a derivative d x mu of some object. Let's call it d mu of some operator omega, which depends on x. And the omega operator is some linear combination of all the generators here. A and A dagger of P, and all the lambdas, in particular of the lambda equal 1 and 2 terms, they contribute because there are non-vanishing matrix elements between L and 1, 2. Therefore, the physical A's, they appear here in the sum, and so the point is that the Lorentz transformation of this extra part of the field operator can be written as a total derivative of some complicated operator expression. And so that brings us to the conclusion of the chapter. So therefore, if you drop this term from our field operator, then you get a negative problem. So let me write this u dagger of lambda times the physical A mu of lambda x times u of lambda. That is on the one hand indeed lambda mu times A nu of x. That is what we want. But from this discussion, we get an extra term plus d mu of some operator omega, which is an operator which depends on everything, in particular also on the Lorentz transformation. And therefore our field operator, which consists only of physical degrees of freedom, does not covariantly Lorentz transform. But what is the problematic term? The problematic term looks like a gauge transformation. And so that is how you see that you can repair Lorentz invariance by imposing gauge invariance. And I think that is what we will start with tomorrow with this little discussion. And then tomorrow we collect all the informations that we now have and form hopefully a uniform, consistent picture. Okay, so let us stop for today and continue tomorrow with this topic.
طيب عرفنا الان فيزيكال او الاس او الاستقطاب استقطاب من تايب من النوع اكس اس يعطينا اس بين زيرو. طيب الاستقطاب من نوع ال يعطينا شيء غريب، يعطينا كما ذكر هو جيج انفاريانس، يعطينا جيج انفاريانس، شيء ما له علاقة بالجيج انفاريانس، ما معروف ما هو، لكن شيء ما له علاقة بالجيج انفاريانس. والجيج انفاريانس هي تعتبر عميقا داخل نظرية علي يوسف، لأنه نظرية علي يوسف تقول أنه داخل التفاعلات فإن السيمتري جيج انفاريانس سينكسر تماما. طيب إذا المحاضرة القادمة ستخبرنا شيئا عن هذا الأوبريتور الغريب أو الاستقطاب في اتجاه L. طبعا الاستقطاب في اتجاه L يعطينا ماذا؟ ما هو؟ هو استقطاب في اتجاه S في حالة الإبسلون كبيزيس إليمنت يعطينا كتلة وزيرو اللي هو المشتقة الزمنية، والأما المشتقة المكانية زيرو، حتى تكون الإبسلون اس عمودية على أورثوغونال على بقية الأوبسيلونز، فإننا نعتبر ذلك. والمشتقة الزمنية طبعا يعطينا سكيلر مباشرة، يعطينا ما يسمى بالتشارج دنسيتي أو الماس دنسيتي، لكن لا يعطينا سبين، لهذا يقال انه سبين زيرو. هو جسيم غريب جدا موجود جسيم غريب جدا يكون موجود في الطبيعة، لهذا نعتقد انه موجود فقط في داخل التفاعلات، لكن ليس موجود في الطبيعة، ليس كفري بارتيكل، لأنه فري بارتيكل لديه سبين، ولأنه السبين يساعد على ضبط الكتلة. السبب الذي يجعل الفري بارتيكلز له سبين هو أن السبين يساعد على ضبط الكتلة بالإضافة للطاقة الحركية، لهذا أنا قلت أن السبين يحدد شكل الكتل. نجد أن الWZ لديها سبين، لكنها أيضا مثل هيجز داخل التفاعل، لأنه السبين بتاع سبين لها عالي بسبب أن كتلتها عالية. الفيرميون السبين له متوسط اللي هو هاف، بسبب أن كتلته ليست عالية، بالرغم أنه يتصرف كثقب أسود. إذا كان الفيرميون يتصرف كثقب أسود فمن باب أولى WZ يكون ثقوب سوداء أيضا، لكن الفيرميون يتصرف كثقب أسود متى يتصرف كثقب أسود؟ عند الأبعاد الصغيرة جدا بمقارنة بنصف قطره، بمقارنة بأبعاده. يعني البروتون رأينا يتصرف كثقب أسود إذا كان الأبعاد حدود 10 أس ناقص 19 10 أس ناقص 20، وأبعاد البروتون هو 10 أس ناقص 16، هكذا يتصرف كثقب أسود. الإلكترون أيضا هو 10 أس ناقص 19 يكون يتصرف كثقب أسود، عندما 10 يساوي 10 أس ناقص على ما أعتقد 21 22 وهكذا. لكن WZ مباشرة تتصرف كثقب أسود، ومباشرة الفضاء الثانوي الأبعاد تقوم بتحليلها إلى عناصر أخرى أكثر استقرارا، أقل كتلة وأكثر استقرارا. وهذه العناصر اللي هو الW يعطينا ميون ونيوترينو، والزي يعطينا ميون وأنتي ميون. الهيجز أيضا بسبب أن السبين له زيرو، هذا يعني أنه يتصرف أنه يتم تحليله أيضا مباشرة، لأنه لا يستطيع أن يوجد كفري بارتيكل في الفضاء الحر، لأنه ليس لديه سبين. الثاني ماذا؟ هذا بالنسبة للسكير. أما ال الإير يعتبر عمودية على الثلاثة، وإذا كان عمود على ثلاثة أنواع من الاستقطاب فإنه ليست حقيقيا، ولكنه هو طبعا حقيقيا لأنه عمود على الإس برضه، فهو يعتبر أحد الثلاثة للفرميون. ال يعتبر أحد الثلاثة للفرميون. لكن بالنسبة للماسلس نحن جعلنا ال هذا ليس حقيقيا، بحيث أنه جعلناه يعتمد على ال1 2 اللي هو النوعين الآخرين من الاستقطاب، وبما أنه يعتمد على 1 2 فهذا يجعله حقيقيا. وبالتالي اللي سنكتشف في المستقبل في الحلقة القادمة ماذا يعطينا هذا ال سنحلله إن شاء الله كما حللنا الإس وحللنا ال1 2، سنحلل ال أيضا إن شاء الله. ولاحظ أن الفوتون يتفاعل كهرومغناطيسيا لأنه كتلته صغيرة جدا جدا، فإنه يتفاعل كهرومغناطيسيا. والإس كتلتها عالية جدا جدا، وهذا ممكن أن القوة الكهرومغناطيسية تنتج كتلة. طيب ماذا عن ال يجب أن يكون له علاقة بالكهرومغناطيسية، وأيضا يعطينا فرميونات. طيب ماذا عن ال سنكتشف إن شاء الله في الحلقة القادمة. السلام عليكم.